So, hey, ladies and gentlemen, thanks for turning up to have a chat with me today. My name's Chris Jackson. For those of you who have never heard of me or met me before, if you need to learn more about me, then of course, you can access my details in ascendoreliability.com, which I know you know how to access. So today we're going to be talking about statistical process control. We're going to be hopefully answering the question in part, what is statistical process control? Now, some of you might have had some or no experience with SPC, which is the acronym for statistical process control, and some of you who have had experiences might have mixed emotions about what statistical process control is all about. So before I do anything in regard to into really getting into what statistical process control is, we need to really ask ourselves what is a process, because the middle word in statistical process control is process. And a process is a set of interrelated work activities that transforms inputs into outputs, which is a wonderfully textbooky definition, which makes our hearts turn to stone and our eyes turn upwards. So let's look at what a process is. And I'm guessing many of you come from organizations where you have processes and are hence interested in learning about what statistical process control is all about. And processes are, without a doubt, the best thing since sliced bread. Now, I'm not sure how widespread that saying is outside of my native Australia. Who knows? It could be across the world, and you know exactly what I'm talking about. At least where I come from, sliced bread is used as a yardstick of a really useful, really wonderfully valuable thing. We so often say the best thing since sliced bread. Sliced bread has been around for a long time. And when we started learning how to make bread and then slicing it up, we could make these wonderful things called sandwiches. And for that reason, bread is one of the most dominant foods across the world today. So imagine you're working in an organization that makes sliced bread. So you can see here that perhaps you or your customers might be interested in things like the overall mass, the airiness of the bread or the crust color, perhaps a number of slices that each loaf of bread has, perhaps the thickness of the thinnest slice. We always hate that really tiny wafer thin slice of bread at the end, the heel of our loaves, as they're technically called, or the crusts. And perhaps some of us are interested in making sure that the differences between the largest and the smallest slices of bread are very small. Why? Well, if you have children who go to school and you make sandwiches, it's really useful having a single loaf of bread whose slices are all roughly the same size, because you make sandwiches for your children. And if those slices are about the same size, they're much more easy to store, cut, wrap up, so on and so forth. But if one slice is twice as big as the next slice, it's really hard to make a sandwich. So suffice to say, there are so many different things that people might find valuable in a loaf. But from a manufacturing perspective or a production perspective, we're not just interested in how good it tastes or how the geometry of the slices. We're also interested in how much it costs to create a loaf of bread, which can be based on all sorts of things like things we call scrap, where we have to throw away loaves of bread or things we manufacture because they don't meet certain criteria, or we need to test them. So we don't want to have to throw away too many loaves of bread. Of course, we want to have a significant throughput. We want to make sure that our factory, our production line, our bakery is able to create or produce a large number of loaves every hour. But these days, we're also interested in reducing our carbon footprint, minimizing environmental waste, so on and so forth. Now, these are outputs or outcomes, whatever you want to call them, of our process. But our customer is not directly interested in the carbon footprint. They might be indirectly interested, but when they're buying a loaf of bread and they're evaluating that product, these things are secondary concerns. And so we are creating bread for a reason. We're creating bread to be profitable. But bread of itself doesn't generate value. If you have 1,000 loaves of bread, that is the value of those loaves of bread isn't a lot, and that value is going to decrease very quickly depending on how quickly you can sell that bread. What I'd be much more interested in is the manufacturing facility, the bakery, the production plant that creates these loaves of bread, because that equipment, how we come up with making these loaves of bread, is what generates value. And that is the process that we're going to look at in this part of the webinar. So a process can be absolutely anything, and it usually involves something doing something else to a bunch of inputs. Now, we are technically minded beasts, even the more artistically flavored human beings, when compared to other primates or other mammals. Human beings are very technically minded, and we inherently prefer processes like algebra and arithmetic, where if you have one input, you get one output. This is what we crave as human beings. But unfortunately, the real world isn't like that, because sometimes we have random processes where for the same input on Monday, we'll get one output. We put the same input on Tuesday, we get a different output. Same input on Wednesday, we get a different output again. In fact, random processes rule the world. And that applies to our poor old bread manufacturer or bread producer, who for all the inputs they try to control for their bread production line, every single day or every loaf of bread will be slightly different. So the loaf of bread in this case is the output. So each loaf of bread will be subtly different. So a random process involves products which are different, and by extension, product characteristics that differ. So for example, the weight of each loaf of bread, the chewability of each loaf of bread will be subtly different, even if they are generally similar. Then there are process characteristics, which are the things that we talked about previously: throughput, production time, yield, scrap, all those wonderful characteristics that, all those values that mean something to us, the producer of these loaves of bread. Then there's byproducts, which includes scrap, waste, exhaust, so on and so forth. And of course, there's not just one set of input. We can control the inputs. In fact, we can have a bunch of different inputs which might be able to have beneficial outcomes. Maybe we want to create a loaf of bread which has this flavor on Monday, but a different flavor on Tuesday. And so when we're coming up with this process, we can control a good number of these inputs with the design of the process itself. Any of us who have worked in manufacturing, if we have an idea for creating something, we designed the process that turns those raw materials into something really amazing for our customer or our user. So we control the process design, which inherently controls a good number of inputs. How fast can our machines make bread? What is the maximum size of the loaf of bread these machines can make? That's part of the production process. And then there's also other things which we find frustrating, such as what we call random noise, which are changes in the certain inputs or characteristics that we can sometimes struggle to control. Now, you can see there's an arrow pointing from process design to random noise, because we can control this noise to an extent. So for example, climate, we can control the climate within our bakery to an extent. We can have air conditioning, we can have humidifiers or dehumidifiers, so on and so forth. But there's always going to be an element of uncontrollability when it comes to climate within the bakery itself, even though the overall temperature might be 23 degrees Celsius or 73 degrees Fahrenheit. It's not going to be that temperature anywhere near the oven that bakes these loaves of bread, I should say. But then there are controllable factors. And these are things that we technically minded people, technically minded species tend to like thinking about. And that could be things like temperature, general settings, the type of technology we're going to use, so on and so forth. And then, of course, there's the raw materials, which themselves have their own characteristics. You can have flour with different gluten concentrations. The yeast can be different. The yeast is a bacteria which ferments to create this wonderful bubbly cell structure in bread. There's lots of different types of yeast. There's improvers, which are different chemicals which can change the characteristics of bread. They're becoming less and less popular these days. And of course, there's things like water, which are very important. Of course, the other input we have to throw into our process are resources that really involve time, people, energy, and let's just call it knowledge. And people and knowledge are very, very obviously important. In fact, knowledge doesn't exist anywhere else outside of the human brain. You might think Wikipedia contains knowledge. Well, that's wonderful, and you're probably not wrong from a certain perspective. But unless you're able to read the Wikipedia page, interpret what those symbols mean, and understand the context for those for principles contained therein, it's not knowledge that is usable. So human beings are a really important input for any process. So many of you, like I first guessed, probably come from organizations which have processes. And although the chances of any of you being involved in producing sliced bread is somewhat slim, you should hopefully see some similarities or parallels between your process, the process in your organization, and the illustration on the screen right now. I dare say you can probably come up with certain inputs and controllable factors and raw materials and resources, et cetera, et cetera. You could probably think about random noises that ruin your day. This is where uncertainty comes from. And of course, the outputs of your processes, the things you're making, or frustratingly sometimes vary around a different, have characteristics, I should say, which vary around perhaps some central values, but there's always going to be some uncertainty. And your program directors, your project managers, your accountants, your finance people, they're interested in process characteristics. What is the yield? What is the uptime? What is the running cost? What is our throughput, et cetera, et cetera. Now, some of the more eagle-eyed of you might have noticed that there is a sneaky little perhaps flaw in this illustration, because we have on the left-hand side temperature as a controllable factor, and on the right-hand side we have temperature as a process characteristic. Now, question for you guys: how can temperature be both a controllable factor and therefore an input, and a process characteristic and therefore an output? So if any of you have got any ideas how we could have temperature on both sides of our process, please feel free to raise your hand and answer verbally, or put your answer in the chat window for all of us to share. And I've just noticed by looking at the chat window that Fred has shared the workbook for today's webinar, which I should have mentioned from the very, very start. My apologies. There is an editable PDF document to accompany this webinar, so you don't need to take notes furiously. In fact, there are spaces in that PDF for you to take notes electronically. So let's go back to the question I'm asking: how can temperature be a controllable factor and a process characteristic? Anyone brave enough to hazard a guess? Baked bread temperature versus output temperature of machinery. I really like where you're going with that. It's a great answer. I'm not going to respond too greatly in too much detail, because we're about to go through an example which is essentially based on that that tidbit. Is there anybody else who can either concur, disagree, expand upon what I think Adiola suggested might be the reason we see temperature on each side of our process, it being an input and an output? How about we just see a thumbs up or a show of hands for people who essentially agree with the principle that Adiola has suggested in the chat window? Dwayne's a fan. So is Wayne. Elise, set temperature range versus actual temperature. Love it. I think you're in the very similar ballpark as Adiola. So yeah, I think you guys are on the right track. So let's look at what this might mean for our bread producer. Now, what this device here, what this machine here is, an intermediate proofer. So for those of you who have been involved with baking bread in the past, or any sort of baked goods, we often mix our raw ingredients, which includes flour, water, and yeast, into a dough ball. And that dough ball then sometimes gets what we call proofed or raised. And what that means is the yeast that is the living creatures inside inside our dough ball, they will feed on the carbohydrates and any sugars and sometimes fats in order to essentially live. But one of their byproducts is carbon dioxide. And that carbon dioxide gas creates those wonderful bubbles, those cell structures within our bread. That's what makes bread really, really different to most other foodstuffs. But sometimes we only want our yeast to create a little bit of carbon dioxide. So this dough ball will go into an intermediate proofer, and the dough ball that comes out the other side will use the yeast and carbohydrates and water along with time and the temperature to ferment, create those gas bubbles, and result in a slightly bigger dough ball at the other end. Now, eventually, we want that wonderful cell structure. And the reason we do this is because the new dough is what we call relaxed, and the gluten can be molded. So we can now take this bigger dough ball and change the shape of it, put it in a tin to create that rectangular shape of loaves of bread we are very familiar with. So that's what the intermediate proofer does. And the dough ball goes through essentially a mini conveyor belt where we can set the temperature. Now, we want the temperature to be between 29.4 degrees Celsius and 26.7. If it's too hot, what will happen is the dough will not be able to hold the gas bubbles. And that's a bad thing because essentially the gas escapes and we don't get the effect we're after. If it's too cold, the yeast can't create enough bubbles. And of course, we can control how long our dough ball goes through. So on the left-hand side, you can see how temperature is an controllable factor. The dial on our intermediate proofer can be changed with a human hand. But the actual temperature within our intermediate proofer will inherently vary. We know hot air rises, so you would reasonably expect the top part of our intermediate proofer to be naturally warmer than the bottom part. And of course, our intermediate proofer needs to have its own internal circulation system to make sure that the lowest part, the bottom part of the proofer, is warm enough for the bread to ferment. So you can see here how temperature, just the way I think Adiola and Elise suggested, and a few of us agreed, that we can set temperature, but there's a difference between what we set and what might actually physically occur. Because of course, we have all sorts of thermostats and thermocouples and different devices that are required to measure the temperature inside, provide some sort of feedback to a circuit board, etc., etc. So now we're coming to terms with what a process is, what an input or controllable factor could be, and what a product characteristic or a process characteristic might be. So before I move on, are there any questions about processes? Feel free to put those questions in the chat window. If there are no questions, of course, I won't see those questions in the chat window, and we'll move on shortly. Okay, so let's talk about making good bread, high quality bread. And when I run my statistical process control and process capability analysis training and manufacturing training, I always focus on sliced bread because sliced bread is such a universally understood product. We've all had experience, even if it's not with sliced bread, with bread in general. And at the very least, we can all appreciate good food. So let's start with the product characteristic of our loaves of bread that matters. And if you think about what it is that you like in a loaf of bread, I'm sure you can think of some characteristics that matter to you, of course, beyond the price. So the characteristic I use in my lessons involve this weird metric, called chewability. I love chewability because it sounds weird and abstract, and in many cases it is. It's essentially a measure of how chewable your bread is. Now, how do we measure the chewability of sliced bread? Well, we have this thing called a texture analyzer, a very expensive machine. And what we do is we put 2 slices of bread on a little table under this machine, specifically beneath a 25mm or 1-inch diameter probe. And what we will do is we will set a certain strain. So for example, let's set the strain to be 25%. That is, our texture analyzer is going to push down until it has depressed our 2 slices of bread by 25%. And the whole time it's measuring the force that our bread exerts back on the probe. And once it hits 25% strain, it immediately pulls out, all the time measuring the force exerted on our bread. You can see at the very end that our bread, in fact, it sticks to the probe a little bit and sort of sucks it down as it goes past the original starting point. Then we wait for a little bit and we do exactly the same thing again. Our probe is then pushed down 25% strain, and you can see here that the force profile is a little bit different. There is a lot less force being exerted as it gets pushed down the same depth. And then the probe is withdrawn again, all the time measuring the force. And we have this force profile associated with our texture analyzer. So what can we do with this? Well, this allows us to help us work out this thing called hardness, which is a maximum force exerted onto our probe as it gets pushed into our bread. And this is measured in terms of newtons. So we can measure the hardness of our bread. And then we can measure the area beneath the first hill or mountain in our first force profile and the hill in our second, area in the hill in the second. And essentially, the difference between these 2 areas represents how much damage our bread has experienced when it was compressed by 25%. And so this thing called cohesiveness, which is a measure of how much damage has occurred, or its ability to withstand damage when a probe or the teeth of a human being are inserted unceremoniously into our sliced bread, is simply the ratio of the smaller area compared to the first one. And so we now have cohesiveness. And then there's another thing as well, which we call, which is based on the time it takes for our probe to be inserted 25% strain in the first, it first gets pushed in, and the time it takes for our probe to be inserted 25% or compressed 25% for our second test. Now, the reason why these times matter is because the probes are being pushed down at the same very slow speed. So essentially, these 2 times represent how long it takes for it essentially or how long our probe is experiencing force, which is a crude measure of the extent to which our bread springs back to its original shape. And so springiness is simply the ratio of the second time divided by the first time. Now, chewability is the product of these 3 metrics. So we can actually come up with a numerical value for chewability, which is fantastic. And this, through experimentation with human subjects, has been shown to correlate with what humans tend to associate with good chewability, for whatever that means. But the reason we want to do this is because, the reason I like using this metric is because although it's abstract, although it seems weird, although it seems very subjective, which tends to turn us technically minded people off, we can always, and I do mean always, find some way of objectifying it so we can come up with a number, in many cases, a very repeatable number that allow us to monitor product characteristics as we go through our production process. So let's now look at the act of actually making bread and being interested in the chewability of our bread as we start baking it in our manufacturing or manufacturing facility. Most people in the industry call it a bakery. So what I'm going to do now is introduce this set of axes. On the horizontal axis, we have production schedule, or however you measure time. So on the left-hand side of this axis, it might be analogous to the start of the shift on that particular day. On the right-hand side, it might be the end of the shift. or perhaps it could be the start of the year and the end of the year, or whatever time scale works for you. And on the vertical axis, we have chewability. And of course, as we bake bread, the chewability of all our loaves of bread will never be exactly the same. So if we pause our production process here and examine the chewability profile of our loaves of bread, you can see that we have this random fluctuation. And we call this fluctuation noise, or variation from common causes, or natural variation. Now, I've seen different textbooks and different experts use these terms interchangeably. So this essentially refers to variation which is predictable probabilistically. We know what the variation is going to be for our process. It's based on constantly active phenomena. It's variation we historically expect. The difference between high and low values are insignificant, and that has a lot of that means a lot of different things to a lot of different organizations. Essentially, this variation is variation we are okay with. We cannot fine-tune our process, or don't want to fine-tune our process any further to limit this natural variation, this natural randomness in the chewability of our bread. And this is okay in many real-world scenarios. So we see this variation, this dispersal from what appears to be a relatively straight line. Hopefully you can agree with me that although we have some random variation in the chewability of our loaves of bread, with each loaf of bread having a slightly different chewability when compared to the previous one, you see it tends to vary around this single line in the middle. And depending on who you speak to, this is often called the signal or the process center. And so we're already starting to look at our data from the perspective of how much it varies, the variation, the dispersal, away from the process center or a signal. So there's two really unique ways of looking at this data set. So let's just say we keep baking bread, and then the chewability of our loaves of bread will obviously change over time. But when we start looking at our data now, we say, hey, something's not quite right. Maybe the chewability is too high. It needs to be lower. We know it needs to be lower. Although our process is clearly what we call in control, it's not out of control. It's doing, it looks like it's behaving in a very expected, predictable way. Maybe our chewability is not where it needs to be. Maybe it's just too chewy, which can happen. And so we use our knowledge of baking bread to perhaps modify some process input and to reduce the chewability of our bread. And when we do that and keep our process going, we start turning down this setting, the chewability goes down. This is what we call influence, where we turn a knob or change a setting in an attempt to positively change a process or product characteristics. But this is based on knowing how to make things happen. So a baker will know what they need to do in terms of yeast content or temperature or time in the intermediate proofer, et cetera, et cetera. They'll know all the different things they can potentially change to reduce chewability if they have observed that the process or product characteristic is not where it needs to be. However, what happens if we observe this data, but we didn't change any controllable factor? What if we didn't change any process input, and all of a sudden the chewability of our bread starts to go down? That is bad, because it is doing something that we don't control. Our process starts being what we call out of control. And then, of course, it's not just where our process center goes to. What happens if the variation, what used to be natural variation that we were happy with, what happens if that variation all of a sudden starts really deviating from the central process center, I should say, in ways and amplitudes that it wasn't before? That could be bad as well. This is what an out of control process looks like. This is not good. And this means that we have potentially variation for what we call special causes or assignable causes, where it's it's emergent or previously downplayed phenomena. It's unpredictable probabilistically. And perhaps there's new and or anticipated behaviors in our process. Our bread is doing stuff it's not supposed to. It's outside of a historical experience. And there's evidence or knowledge of some change in the process. We don't just have to wait for our chewability data profile to come back to our office for us to observe that perhaps one of our machines is on fire, or perhaps it's vibrating in ways that it wasn't vibrating before. So this is what we are trying to avoid. Essentially, what we're looking at here is a stable or in control process on the left. Something happens at this point in time, and then after that, we have an unstable or out of control process. Now, out of control means one thing. Being bad means another when it comes to manufacturing. Let's just explore that for a few minutes, because being out of control is clearly bad. So what am I talking about when I say transitioning to bad? Well, if we go back to our bread, we have chewability, and through perhaps lots of trials with prospective customers and experts in the field, we work out what too chewy is. That is, we have some upper limit at the top of this upper limit on chewability, which implies that if we go beyond that limit, our bread is not good. Conversely, we might have some lower limit on chewability where our bread is not chewable enough. And in the middle, we have what's called good bread. Now, I'm not going to go into what this means philosophically in too great a detail, but this binary approach to good versus bad is not particularly useful, and organizations who make high quality products don't simply look at bread which is just slightly within these limits as good versus bad, whether it being slightly where bread is slightly out. I'll try and explain that a little bit better in the next minute or two. We call the upper limit the upper specification limit, and the lower limit the lower specification limit. So although those organizations who do this really well don't simply say bread is good if it's within these limits, we are trying to always focus on high quality bread, which also has a benefit of us being able to produce bread a lot faster and a lot less expensively as well. So we'll often see these things called upper and lower specification limits, or the USL and the LSL. So if we superimpose the chewability of our profile of our loaves of bread within this range, you can see that our bread loaves seem to be okay at the very start of our process, but all of a sudden we have some problems where loaves of bread are now being baked and they're clearly outside of the specification limits. This is what we call defects, or these are what we call defects. Sometimes we call the bread that is resulted from this process defective or bad bread. And each different industry has its own set of terms to describe what bad products look like. But this is the outcome of a process that is out of control. Eventually, it's going to start creating bad products. When I say eventually, that's a very important word I want you to remember, because statistical process control is all about trying to prevent bad things from happening. Now, remember, this is where our process was stable or in control. This is where something happened to push our process out of control. And this here is our first instance of bad bread. So what usually happens is our process is out of control well before products start becoming defective. In fact, this time period here could be days, weeks, or months of early warning if you know where to look for it. So what we want to do is work out when our processes start coming out of control before we have something bad happen. Now, plenty of us have been in organizations where we have to put out fires. We just got word from the final inspection team that the first 10 products that have just come off this production line are outside of specifications. That usually involves a crisis. From the CEO down, everyone is focused on the manufacturing team. They are pressured to get a fix out there as quickly as possible, because until they do, they can't restart the production line. They can't make money or generate revenue by selling these products to customers. As you can imagine, and some of you have been in those situations, trying to come up with problems in these scenarios are incredibly stressful and taxing. Sometimes when we come up with solutions, we will get lauded as heroes. We call these firefighting heroes. But even firefighting heroes who do get a kick out of being the guy or the girl who solves problem under immense pressure, they are really limited in terms of the solutions they can come up with. They are pressured to find really quick solutions which inevitably have minimal long-term benefit. So when we keep responding to fires, we come up with band-aid solutions, which means there's going to be a fire next week, so on and so forth. And then we have a culture of firefighting where the highest performers in the organization are those who are seen to be the best firefighters out there. Now, instead, it's much more desirable to have early warning of your process coming out of control, so you can casually and with little stress survey all the options open to you, come up with the best one, which has a long-term effect. It might even need a little bit of time to implement. And if you can do all this before you start producing what we call bad products, then you have a wonderfully more robust process, which is less likely to produce defective products in the future. That's the sort of organization we want to aspire to. And that is where statistical process control helps. Because statistical process control is all about looking at statistics of processes to give us these days, these weeks, these months of early warning before something bad happens. Now, what I'm not going to do in this webinar is go through standard deviations, this and bell curves, that, and all sorts of other statistical stuff. The reason I'm not going to do that is because most students who I come across, who especially do my courses, they want to quickly work out how to come up with numbers. The problem with that is they don't understand why they are doing this. They don't understand what they're trying to achieve, which means they go back to their organization and they come up with numbers and they don't understand what they are trying to do, which is all about early warning, trying to get as much time as possible to identify that there's a problem before bad stuff starts happening. And so I've been involved with organizations who are great at coming up with numbers, but they never inform us any decisions, any root cause analyses teams to get in there and solve problems before bad stuff happens. We still have these numbers being generated, but the organization tends to only react when bad bread is manufactured. We don't want that. It's a waste of time doing an SPC course if all you focus on is the numbers and not why you are doing it. So let's dabble with statistics though. I know we all love statistics, but let's just do a little bit of dabbling to look at what statistical process control can mean for us. So what I'm going to do now is I'm going to use statistics, specifically this red region here, which represents a range or region where 99 or over 99% of our chewability values fall within. And this range comes from the data we are gathering from our production line. And you can see here that on the left-hand side where our process is in control, our region of 99% of chewability values is very consistent. It doesn't change from left to right, but as soon as our process starts becoming out of control, this region is very, very problematic. So what can we do? Well, if we go back, if we start our manufacturing process, our baking process, our production process, and we really work hard on keeping our process in control, and we get data from that in control process, we can come up with the region where 99+% of chewability values will lie for our stable or in control process. And we call these things upper control limits and lower control limits. And you can see they are different to the specification limits, because the specification limits are based on human interpretation or definition, I should say, of what is good versus bad. A control limit helps us work out what a capable system looks like, what an in-control system looks like. It sort of helps us work out or identify if our system is doing, or a process, I should say, is doing what we expect to do, which includes having natural variation, but within certain parameters. And when we have these control limits, when we have these lines on this chart, it's really can be really useful in helping us identify from a statistical perspective when our durability values start to deviate from what we expect. And so control limits are great at giving us early warning for our process coming out of control. Now, there are lots of other little nuances. There's regions, there's zones. In fact, there's 8 statistical rules which are based on upper and lower control limits, where if we gather data and if we see our data break any one of these rules, we then have cause to suspect that something fishy is going on. And in fact, our process might be coming out of control. And this is an example of what we call a control chart. Control chart is a graph used to study how a process characteristic changes over time. So an example of and there's plenty of control charts out there, an example control chart looks like this. And here is raw data from our bakery where they have measured the loaves of bread, measured the chewability, I should say, of our loaves of bread over the production schedule. And each one of these blue dots represents raw data points. You might notice that this raw data isn't very smooth. You might look at this data and say, you know what, even though it's not very smooth, even though it's a lot of variation, maybe, just maybe, there is some sort of central process center, I should say, or some sort of signal. And we know, for those of us who've done statistics, that the mean or the average is one estimate of measuring central tendency. So what we want to do is turn this cloud of dots into something that is easier to visually interpret using our own very flawed human eyeballs. So what I'm going to do now is I'm going to take or break up all this raw data into samples. Now, all these bars on the data points right now contain 4 data points. So each red bar contains 4 data points, and each white bar between 2 red bars also contains 4 data points. So what I'm going to do now, I'm going to focus on each sample of 4 data points lying within each bar. And when I do that, I can take the mean of each one to come up with these red dots here. Now, these red dots, if you were to draw a line through them, are a little bit smoother. And that's the beauty of taking means or averages from samples. In this case, it's from 4 data points. If I want to really identify the mean or the central tendency of our process, we can increase the number of data points we sample. So go from 4 data points to 10 or 20 or whatever your process allows. And those red dots will start, if your process is in control, will start moving a lot closer towards a process center. So at the very least, you can see how finding means or averages of the samples of data points makes this chart a little bit smoother when we superimpose those sample means over the top of our raw data. Okay, so what's next? Well, we know that our process can come out of control when our process center changes, when our chewability starts plummeting downhill. That's a bad thing. So you might look at this line drawing our sample means and say, you know what? I can see it goes up and down a little bit, but it does seem to go around a central value. So that's a good thing, which it is. But the other part to out of control processes are those processes where the variation, dispersal, starts going out of control. So this is dispersion. And you can see here that in our raw data, we have a fair amount of dispersion that is not always captured in those mean data points for each sample. By definition, the mean of each sample is trying to filter out dispersion. But we know dispersion can also creep into our processes and force our systems out of control. So what we can do is go back to each sample and calculate the range for each sample. And these red lines on the chart now, they represent the difference between the highest value in each sample and the lowest value in each sample. And this estimates the dispersion within our process. And so what we can do is separate this now confusing chart into what we call an X bar R chart. And the X bar R chart is actually two charts. The top chart involves the mean of the observed product characteristic. And you can see the red circles, which represent the mean of each 4 data point samples. They are the red dots which we plot on our X bar chart. And the bar on top is how we represent the sample mean. And at the bottom, we have R, which represents the sample range. And so the idea is that this now visually represents the random nature of our process. And again, if you're still interested in statistical process control after this webinar, you then need to go and do courses on how to learn how to first create these charts and then interpret these values. Because in this case, this X bar R chart represents a system that is, or process I should say, that is in control. There is nothing to be concerned about here. And if you were to use the rules, those 8 rules that statistical process control is based on, those 8 rules would essentially all be met or passed. And you would then conclude that our process is in control. There's nothing to be worried about as of today. One of the biggest issues we have in manufacturing facilities is people overreacting. You get one data point which is slightly unexpected, and all of a sudden we turn the temperatures down, we turn the speed down, we turn everything down. The problem with that is this is still a random process. It is feasible for a process that is in control to spit out values which you would not inherently expect just because there is a random process going on. So SPC charts, perhaps their most useful, or control charts, I should say, perhaps their most useful function is giving us the confidence to not react when something slightly unexpected happens as well. Because if we create these charts and use those rules, we can walk away with a great deal of confidence that our process is in control. Conversely, if our process is not in control, these charts make it very obvious. So on the horizontal axis, though, we're going to replace production time with sample number. So whenever you see X bar R charts, they contain these two charts where the top is full of X bars, which measures the central tendency or process center. And the bottom is full of Rs, which measures the dispersion or natural variation. So I'm going to show you a basic example of some statistical process control using a control chart, which allows you to oversee your process and work out what might be going on. So let's just say that you work in this bakery and you have collected a ton of data for the chewability of your bread. You can see on the screen, you have a bunch of samples, 1 through to 25, and perhaps what these samples represent is you going to your production line every hour, taking 5 loaves of bread, going away, testing those 5 loaves of bread using that texture analyzer to come up with data points so that you can track how the statistics associated with your bread change over time with respect to production or baking. Now, if you go and do a control charting course or a statistical process control chart course, you'll almost certainly be taught how to create an X bar R chart. And here is the X bar R chart for that data set. Now you can see here, this is done in software that I use. We have the upper and lower control limits for each statistic. Now remember, the control limits essentially help us work out what we should expect. Now in this software, you can see that the X bar chart at the top has superimposed some red lines and red dots. And the reason it's done that is because some of the statistical rules we use have been violated by this data set. Now, question for you guys out there, can you see any point where you think, or any point in these charts which might coincide with an event where our system starts coming out of control? Anyone see any points or any parts where these charts might suggest that our system is starting to come out of control? Anyone brave enough to say, yes, I can see it coming out of control, or no, I can't? And if the answer is yes, specifically, where might that issue have started occurring? Well, there's got to be someone brave enough even to just guess. Correct, Adiola. It's depending on the rules you use. Some people use 7, but one of the rules is having 8 points in a row above or below the process center, which suggests, doesn't indicate, it suggests your process might be out of control. So that's an example of one of the rules which I'm guessing you've heard about in the previous course or previous conversations. And in fact, just for clarity, that is the rule that resulted in that top row of red points and red lines being superimposed on our chart. The question I was asking, where do you think our process starts coming out of control? Daniel suggests, yes, possibly where the last red leads to the blue section. I believe Daniel is suggesting this region here might be the region where it's possible, we might have evidence to suggest our process is coming out of control. Daniel, is that the region you were talking about? Fantastic. Show of hands. Does anyone agree with Daniel and that little red circle on the screen, which indicates indicates there's a chance our system is coming out of control? Elise and Sean. Adiola is happy with that. Fantastic. So obviously this webinar doesn't go through coming up with these the actual statistical process of coming up with these charts, even though I did describe how you do it. It doesn't involve how you use software or Excel or Minitab to come up with these charts. It doesn't involve going through each rule that's where our statistical process, where each rule which suggests that our process is coming out of control. And I can see that Mark is suggesting that all first 12 points are above the mean. So that's violating one of the rules. Yes, that's violating the rule that Adiola suggested. Absolutely. Thank you, Mark. You can also see that we have some issues on the right-hand side where we have some points continually going down as well. So what would you do if you saw this X bar R chart? What would you do given this chart? If we reasonably suspect there's something has happened in that region where I've circled, what would you do as a chief baker or the chief manufacturing engineer or production supervisor or foreman or whatever the title applies to your organization? You see this X bar R chart. What are you going to do if you see that behavior? What can you go and do now? What can you go and do? What do we go do now? We've got some of us doing the heavy lifting in terms of responding in the chat window. If anybody else is brave enough to suggest what we can do now. Daniel, try to find out what might have changed the process. Investigate. Those two answers are spot on. RCA, another spot on example. So what we can do now is we can say, not only do we realize our process might be going out of control, we know precisely when. So let's just say we work at a bakery and we look at our X bar R chart and we realize that something could be happening. Let's just say that period of time corresponds with Thursday or 10 a.m. or March or whatever time period matters. And we go down and we speak to our people and we say, did anything change at around this time? And perhaps one of our people will say, yeah, well, that's when we switched flour from supplier A to supplier B. It should be in specification. It's the same flour, it's the same grade of flour. and we go and investigate further. And maybe we just realize that the flour from the second supplier, although it's within specifications, so to speak, is not the same as the flour from supplier A or the first supplier. What we have now done is potentially averted a monumental issue where we treated one flour as if it's identical to another flour. And yes, that is an issue in baking bread. And we can now do all sorts of things like go back to supplier A or realize that the flour from supplier B, I think I keep mixing up A and B and 1 and 2, but the second supplier's flour, it might need more yeast or more fermentation or higher temperatures in the intermediate proofer. But now we've started a conversation which is stress-free because our system is going out of control. It's doing something we didn't expect it to, well and truly before we start baking bread, which is outside of specification limits. That is what SPC is all about. Getting ahead of the curve and keeping on top of our system, on top of our process, I should say, before bad stuff happens. And you can't do that with the human eyeball or gut feeling. That's where statistics can be really, really, really helpful. And of course, this statistical SPC just gives you points where evidence suggests that something unexpected is happening. It doesn't always mean your process is coming out of control, but it does start the conversation to make sure that if your system is starting to come out of control, you will be the first ones to know about it well and truly before we have to start throwing away loaves of bread because they are outside the specification limits when it comes to chewability. So I'm going to leave it there and open the floor to any questions, any comments, any anecdotes, anything at all that might relate, expand upon, etc., etc. Okay, I see a question. When would the LCL and UCL need to shift closer to each other? When would they need to shift closer to each other? So remember, this is a very troubling principle for people to understand. Specification limits, the LSL and the USL, are a human characteristic. It's what we define good bread to be. LCL and UCL are control limits. So they are essentially define the region in which a stable process will produce products. If it needs to shift closer to each other, that's where we deal with what we call process capability analysis. The only reason they need to start shifting closer to each other is because you have a problem with variation. If your process is, and usually what happens when you start a new process, a manufacturing process, you first get your process under control. If you're manufacturing bits of metal, you get the manufacturing process under control so you know what's going on, and then you work out if your parts are within specifications. You can be under control and outside of specification at the same time. But the first thing you need to do is get your process under control, because that means you then are able to influence it the way you want. At the very start of a process, you need to get your process under control and make sure, for example, the defects within that metal strut are lower than a certain critical value such that your strut is deemed high quality or not. So to answer your question, when would the LCL and UCL need to shift closer to each other is if you do not meet quality specifications. If enough products are being manufactured outside of specification limits. Now, what you want to do is once you get your process under control, once your process is what we call capable, so all the natural variation is within the specification limits, you in a way want to throw away the specification limits and then deal with LCL and UCL only. And the reason you want to do that is because you don't want manufacturing engineers to be confused between the two. Your process can be out of control, but still within specifications. The only things that specification limits can now do will introduce the temptation to say, well, it's outside of control limits, but it's still within specifications. So I'm going to leave it to the next shift to deal with, or somebody else to deal with. I'm going home. You don't want that. You don't want that culture in your organization. So you get it under control, get it capable, and then use LCLs and UCLs for the rest of your process life. Does that answer your question? No worries. Now, Jacob asked that he saw the LCL and UCL in both mean and range graphs, and they were in similar positions. You assume the actual positions will have means and range control limits with differing values. I don't entirely understand the question, but I'll go back to an actual X bar R chart. Now you can see on this one here, on this X bar R chart, you can see that the control limits are a little bit different. You can see in the range control chart, or the R chart, that the blue line, which represents the midpoint or the mean of the entire process, it's a little bit lower there compared to the, or it's below the middle, the midpoint between the UCL and the LCL. And that's because the range varies in its own unique way. There's a special probability distribution, which I don't want to bore you guys with, that describes the nature of how ranges naturally vary in stable or in control processes. So you can see that there is a slight difference between the UCL and the LCLs for each for the X bar and the R chart. So your software, or if you're doing this by hand, you need to take that into consideration, because all these control limits do is characterize the region within you expect 99%, 99.73% to be exact, of your statistics falling within if your process remains in control. Does that answer your question, Jacob? Just waiting for Jacob to confirm. Thank you. James asks, James said, is SPC effective as a detection method or a control plan in FMEA? And the answer is hell yes. It's one of the best ones going out there. Now, of course, SPC can't be a detection method for everything out there, but it is one of the best. In fact, your control plan, the word control is the last word in statistical process control. It is one of the best ways of working out if one of the key, for example, critical to quality characteristics that some FMEAs come up with, if that's something that your customers truly value, then SPC is great at detecting if your process is starting to go a little bit out of control. But out of control sounds bad, and it is bad in a way. Out of control sort of triggers visions of us driving a vehicle, all of a sudden the steering wheel falls off, and therefore by definition, we are out of control. But it can just be something as simple as identifying that the cutting edge for a tool is starting to wear out, for example. So it's not necessarily all negative or all bad, but it just gives you as good a chance as possible of identifying if things like the chewability of your bread, which is a really, really weird metric, is starting to change in the wrong direction. So it is a fantastic detection method, but make sure when you do a FMEA, don't just throw an SPC willy-nilly. Think about the metric that matters. Think about what it is to fail and process FMEAs. Failure modes aren't mechanical or physical. They're more aligned with manufacturing products which are outside of specifications. So make sure that you only use SPC if it's feasible. And of course, SPC requires you to inspect or test products as they come off the production line. If you're only manufacturing one or two products because you're a small satellite manufacturer, then there's not a lot to be benefited gained, I should say, from SPC, because you only have 3 samples. But if you're manufacturing loads of bread by the thousands, then it's very, very useful. If your testing is destructive, that's a con. If your testing is non-destructive, that's a pro, because every time you test, you don't have to throw away that loaf of bread. So think about what it is you're trying to detect, and hell yeah, try and get SPC in there if you can, because it is just so wonderfully fantastic. It's creating those stress-free, zen-filled manufacturing facilities where we continually improve and tend not to have career-ending crises and spot fires. Does that answer your question? I think you've already said yes. No worries. Any more questions? Just that's a show of hands out of for curiosity, more for curiosity at my end. How many of you have been, let's just say, introduced to SPC, but never really thought of SPC in the way we talked about today? Does that apply to anyone? So got 1, 2. And I know some of you are coming here to learn about SPC for the first time. Got quite a few. That's fantastic. Well, it's not fantastic that that hasn't been taught to you previously or hasn't been emphasized previously, but I'm glad that hopefully you walk away from today's conversation with a better understanding of what SPC can do for you and why you and your organization should be feverishly motivated when it's the right tool to use to implement SPC to create that stress-free Zen-like manufacturing facility or that high morale baking facility. Funny how those organizations which do SPC well tend to have a lot of employee satisfaction. Thank you, Adiola. No worries, feel free to use that. And Jacob talks about frequency of product grading and quality control. Fantastic. Obviously SPC, I didn't use the term quality once, I don't think today, but yes, obviously SPC is all about quality when we define quality in terms of defects and proximity to nominal values. Awesome. Well, feel free to keep, if people are typing questions, I'll hang around and wait for those questions to pop up in the chat window. If you have any more questions, feel free to reach out after today. You've got my contact details. More than happy to have a conversation about SPC and how it can help you. And of course, there's another thing we call process capability analysis, which goes beyond SPC to make sure that our process is both in control and within specifications. We call that capability. The first thing you need to do is get your processes under control. There's no point trying to get them within specifications if they're out of control. It's like driving along a highway and your steering wheel has fallen off and you saying everything is okay because we're still on the highway. You know that you're about to have a bad day if you don't do something about that steering wheel lying on the floor. Is Excel suitable to use for analysis, or do you recommend using software? That's a conversation I'll have offline because, that's a conversation I can have with you in greater detail after this conversation, Daniel. I do SPC and process capability analysis, which comes with, when you do that, you get an Excel application. So Excel is more than suitable. You just need to know how to come up with the underlying equations for the charts and everything else. Excel is perfectly suitable, but I'd suggest you need to be an advanced user, and you'd also have to have done an SPC course where you understand where these control limits and these rules come from. So I'm happy to talk to you at greater length about Excel after this because it is suitable with caveats. But yeah, you certainly can use it. Thank you, Carl. Thank you very much for that feedback. Thank you, Golnaz, and thank you, Daniel. So any more questions, feel free to ask them. I think we're about done, Fred. Another thank you. So I think we're starting to see the sentiment changing from no more questions to thanks for coming. Thank you guys for turning up as well. Ascendo really values any feedback you do have, if we're heading in the right direction, or if there's any ideas you have for future webinars that might not be on the calendar just yet. So feel free to throw feedback, both good and bad, because it tells us if we're on the right track or not. But yeah, thank you for your time today. If you do have any questions, you've got my contact details, feel free to reach out. You've got the workbook. No, no worries, Carl. Yeah, absolutely. Bread, fantastic. It is a wonderful, wonderful food that has supported civilizations for eons. Thank you, Longshan. All right, Fred, I think we're good to go.